Hello and welcome. My name is Arya Farkhonde. I'm a master's student at Sapienza University of Rome and a research intern at Computer Vision Center of Spain. Today I'll be presenting our paper on Twar's self-supervised gaze estimation. In this work, we studied the task of 3D appearance-based gaze estimation, a computer vision task consisting of using neural networks to map high-dimensional RGB images to low-dimensional gaze vectors. In recent years, convolutional neural network-based methods have shown great performances powered by large-scale gaze-annotated datasets. However, these supervised methods cannot generalize well to unseen distributions with novel head poses, appearances, geometry, and illumination conditions. A possible solution to this problem is through the acquisition of even larger gaze-annotated datasets with more variability. However, this is an unscalable and laborious process to follow. Therefore, alternative solutions have been proposed, such as using weak supervision. Despite learning more generalizable representations than purely supervised methods, the performance of these methods is bounded by the accuracy of pseudo or noisy labels. Additionally, generative-based unsupervised methods have also been employed to learn usable representations from eye images for gaze estimation. However, these methods require supervision in other forms, such as requiring paired eye images of the same person with a similar head pose. In contrast to previous works, our goal is to learn an informative representations for gaze estimation using large-scale, uncurated, and unlabeled face images collected from the internet. Using face images has proven to be more effective than eye images since it contains auxiliary information such as head pose. We make no assumptions about the kind of data or architecture. In recent years, joint embedding self-supervised approaches have shown great success in learning generalizable representations for image recognition tasks, especially image classification. Similarly, these methods could be employed to learn usable representations for the task of gaze estimation. These methods aim at learning an invariant representation to image transformations, which benefits image classification tasks. In fact, invariance is a desired property for image classification since the label remains unaffected under most image transformations. However, in the context of gaze estimation, applying affine transformations to images results in respective changes in the label space. Therefore, gaze estimation requires equivariance under affine transformations. This is the overview of our method. In the first stage, we learn an unsupervised representation from large-scale unlabeled face images using self-supervised learning, while promoting equivariance property under affine transformations. In the second stage, we transfer the learned knowledge via fine-tuning with relatively small-scale gaze-annotated images. As the pretext task for self-supervised pre-training, we follow the existing joint embedding-based methods. We extract two different views of the same image by applying two different transformations which are randomly sampled from the transformation catalog. Then, we map the views to vector representations using an encoder. We then maximize agreement between the vector representations. To maximize agreement, we employ SWAV, which is an online clustering-based method. SWAV attaches a projection head on top of the encoder to get vector representations. Then, the vector representations are compared to a set of learnable prototypes to compute cluster assignments. Then, a swap prediction problem is formed to maximize agreement. The swap prediction problem is as follows. The computed cluster assignments are swapped and predicted using the vector representations. Intuitively, if these two vector representations contain mutual information, it should be possible to perform such a swap prediction. As previously mentioned, joint embedding-based methods such as SWAV aim to learn an invariant representation under affine transformations. However, gaze estimation requires equivariance with respect to the affine transformations. So, in this work, we answered the question of how to extend current joint embedding-based methods to learn an equivariant representation under affine transformations. To this end, we propose a simple approach SWAT, which stands for Swapping Affine Transformations. To promote the equivariance property, SWAT swaps the transformations applied to images and applies them to the vector representations using a feature transform layer. This process equalizes the vector representations of two views in terms of the affine transformation information. Therefore, argument maximization between equalized vectors no longer forces the encoder to become invariant. Instead, the encoder is encouraged to learn an equivariant representation. SWAT uses a feature transform layer to perform the feature space equivalent of the image space transformation. The feature transform layer takes as an input a vector representation, performs the inverse of vectorization to enable matrix-matrix multiplication with the affine transformation matrix. After multiplication, it applies vectorization and L2 norm to output the transform vector. Here you can see the transformation catalog used in this work. It contains various appearance transformations shown in blue and affine transformations shown in red. Note that our goal is to promote invariance under appearance transformations while promoting equivariance under affine transformations. The only exception is we promote invariance under scale transformation, since this transformation doesn't change the gaze label. For the self-supervised pre-training stage, we consider two large-scale datasets. The first one is the ETH gaze dataset that is specifically collected for gaze estimation under controlled conditions. However, we also consider an uncurated dataset, VGG face, that contains 1.5 million face images collected from the internet. Note that we discard the labels for the ETH gaze dataset. To leverage the knowledge learned through self-supervised pre-training, we perform fine-tuning using labels. To this end, we initialize the weights of the CNN encoder using the pre-trained weights and attach a linear head to regress gaze. In this setting, the whole network is fine-tuned. In our experiments, we also consider linear evaluation, where we freeze the CNN encoder after initialization with SWAT features and only train the linear head with labels. To evaluate the quality of unsupervised features, we perform a linear evaluation. As shown, SWAT pre-trained with the uncurated and unlabeled dataset VGG face achieves the lowest gaze error compared to other pre-training schemes such as SWAV and ImageNet supervised features that is widely used as initialization in previous works for gaze estimation. After comparing the pre-training methods, we switch our focus to evaluating SWAT in the presence of limited supervision. In this setting, we use 10% and 30% subjects of ETH gaze to perform fine-tuning. The results suggest that SWAT achieves about 1 degree less error compared to the baseline with random initialization. Next, we compare SWAT to state-of-the-art methods for gaze estimation. For this purpose, we perform fine-tuning using full supervision. As a baseline, we also train the same network with random initialization. On all benchmarks, SWAT outperforms the baseline, achieving up to 25% improvement. Moreover, SWAT pre-trained with VGG phase outperforms the state-of-the-art methods on 3 out of 4 benchmarks. Note that datasets such as XGaze and MPII phase apply a normalization step to restrict geometric variation, which conceals the benefit of enforcing equivariance by SWAT. Therefore, SWAT shows its superior performance in unconstrained gaze scenarios such as Gaze 360 and MPII phase unnormalized version. To evaluate the generalization capability of SWAT, we perform cross-dataset evaluation, where we train on a given dataset while testing on another dataset. SWAT outperforms the supervised baseline with random initialization on all the benchmarks, achieving up to 57% improvements. Next, we propose the following metric to quantify equivariance. Based on this metric, the representation of a geometrically transformed image should be as close as possible to the geometrically transformed representation of the original image. We compare representations learned by SWAV and SWAT based on this metric, varying rotation degrees as the geometric transformation. we find that SWAT on average achieves 26 and 21% improvements over SWAV in unconstrained gaze scenarios, such as Gaze 360 and MPI phase unnormalized version respectively. We show the estimated gaze direction on the test set of Gaze 360. As shown, this supervised model demonstrates a large discrepancy compared to the ground truth vectors, while SWAT estimations better match the ground truth. It can be seen that SWAT is able to better estimate the gaze direction in extreme head pose conditions. We also show the estimated gaze direction on MPI phase. As you can see, SWAT achieves higher performance than the supervised baseline in the challenging case of extreme illumination conditions. In conclusion, in this work, we explored the effectiveness of a self-supervised method in the context of gaze estimation and proposed a novel approach SWAT to learn an equivariant representation under affine transformations. We showed that SWAT learns more informative representations than other pre-training schemes for the task of gaze estimation. We also showed that our method achieves superior performance in low data regimes. SWAT, fueled by large-scale uncurated dataset, achieves more generalizable results, outperforming the supervised baselines and state-of-the-art approaches for both within and cross-dataset settings. Therefore, our approach can be leveraged to boost the performance of current gaze estimation system in real world via leveraging large-scale freely available face images on the internet. For code and further details, please check out the official repository.